Assalamu alaikum, dear student. Today is the lecture number 1 of week 3 and we are studying the pressure and fluid static, the chapter number 2, and the topic we are going to study today are the case number 4 and case number 5 of basic equation of pressure field that we derived in the previous lecture. In the standard atmosphere or US standard atmosphere, measurement of pressure, manometers, that we are going to study today. So let's see the quick review of the basic equation for pressure field that we derived previously, and this is the final form of the basic equation that we derived in the previous lecture. And based on that, we will see the case number 4 and case number 5, how the things move. So case number 4, what exactly it is? The interconnected vessel. Here is, consider a vessel of two interconnecting branches open from the top and contains homogeneous fluid at rest. So here the interconnected vessel, this is one end of the vessel, this is quite narrow and tall, this is quite wide and little short, and at the both end the pressure P1 and P2 are acting. If P1 and P2 be the pressure acting on branch 1 and 2 respectively, this is the branch 1 and this is the branch 2. The pressure at an arbitrary horizontal plane AA can be expressed as. So this is filled with the fluid and that fluid is continuous. So this is the point where we want to find out the pressure. So what is the pressure here and what is the pressure here? So we derived the equation previously. P is equals to P1 minus P2 is equals to gamma H1. So we want to find out the pressure at point A here. So at this point the pressure, what exactly it is? The pressure P1 PA is equals to P1 plus gamma H1, because the P1 is the pressure exerting on the top. So same here, if you want to calculate the pressure at this point, so PA is equals to this pressure and the pressure exerted by the fluid, as here this pressure and plus this pressure which is exerting due to the fluid is equal to pressure PA. So here it is P2 plus gamma and height of the fluid, which is gamma H2. So the PA and PA pressure for the vessel 1 and PA pressure for the vessel 2 we calculated. Let's move. So comparing both equations, so PA is equals to P1 plus gamma H1 and P2 is equals to gamma H2. So P1 minus P2 will be equal to gamma H1 minus H2 is equals to gamma H. Okay, so this is the pressure difference we will get. But if P1 and P2 are the atmospheric pressure, agar P1 and P2, if the P1 and P2 are the atmospheric pressure, what will happen? Therefore H is going to be 0. It means if equal pressure acts on both free surface, the two surfaces are at the same level. Okay, it means that the concept of equality of pressure at equal elevation is important for both the operation of hydraulic jacks, lifts, press and many other type of heavy machineries, So let's move on. The fundamental idea behind such device is shown in the figure. So consider this is a connected vessel. One area, this is the press, here this is the hydraulic jack, okay, and the force normally we applied, that is a small force, that is F1 is equals to rho A1, because the area is small. The pressure definitely whatever the pressure we will exert, the same pressure will transmit to the other side according to the Pascal law that we have derived previously. So the fundamental idea behind such device is shown in the figure below. So here we are applying the force F1. Okay, the area is small, the pressure we are applying is the small force, and then this pressure is transmitting through the fluid to the other end, which has a bigger area. Okay, so this force F2 is equals to PA. So this is, since the area is more, the same pressure is transmitting here. So we know that the force is directly proportional to area. So this is going to be enhance the magnitude of force. So let's see, a piston located at one end, this is the piston located at one end, is used to change the pressure of the system. Okay, so this is we use to press the fluid. The fluid must be incompressible. If it is compressible, so this will not work. Okay, the fluid must be incompressible. Since the pressure P acting on both piston is same, okay, since the pressure P, because you see the pressure is same, because whatever pressure you will apply, it will transmit from here to other end. Since the pressure P acting on both piston is same, large mechanical advantage can be obtained on both on the other side. Okay, so if we compare यानी कि F1 over A1, F2 over A2, compare pressure equal, so what will happen, F2 is going to be F1 A2 over A1, can be obtained on the other side. Since A2 is greater than A1, so the F2 will be higher than F1, yani F2 will be greater than F1. So that is a small force, because F1 is a small force that we are applying, but because of this technique we are getting a large force at the other end. So that is a small force applied at the one end can be used to develop a large force at the large piston. And same thing we are doing here. We lifted a very heavy truck, cars, by applying a small force on the piston side. So now let's move on the case number 5, the pressure variation for compressible fluid. So here we are going to talk about the compressible fluid when the density or the specific weight are not constant. Normally the gases are being treated as compressible fluid. Since the density of the gas can be changed significantly with the change in pressure and temperature. So this is the equation we derived for the fluid, that the pressure varies as the elevation increases or decreases, and it depends on the density of the fluid. It depends on the density of the fluid. If the density is constant, so it only depends on the height. But if the density is varying, okay, if the density is varying, so we have to apply the integration, because we will treat this density as a variable. So let's see, since the specific weight of gases are comparatively small, then the pressure gradient in the vertical direction is correspondingly small, and even over distances of several hundred feet the pressure will remain essentially constant for a gas. This means we can neglect the effect of elevation changes on the pressure in gases, in tanks, pipes, and so forth, in which the distance involved are small. But for the situation in which the variation in heights are large, on the order of thousands of feet, attention must be given to the variation in the specific weight. The equation of state for an ideal gas is PV is equals to rho RT. where we make a relationship between the density of the gas and the pressure, where P is the absolute pressure, R is the gas constant, and T is the absolute temperature. Combining the above equation with take the derivative with respect to Z. So what we are going to do now, we are going to put the, so to develop the relationship between the pressure and the density, so from here we are replacing the density with P over RT. Okay, so because dP over dz, the equation we derive equal to minus into gamma H into gamma. So here we are replacing density, because gamma is equals to rho g, so we are replacing rho with P over RT. Now we are integrating that at what height we want to measure the pressure or the change in pressure due to the density. So here G is constant, so from P1 to P2, dP over dP, P is, we brought it this side, dP over P is equals to minus, G is constant, R is constant, so dZ over T. Assuming that temperature has a constant value T naught over the range Z1 to Z2. So we are considering the because two changes we cannot monitor at the same time, so here we are considering isothermal condition. Okay, we are keeping the temperature constant. So we are keeping the temperature constant T naught over the range Z1 to Z2 isothermal condition. Then we took the integrative. So ln P2 over P1 is equals to G Z2 minus Z1 over RT naught, or taking antilog of both sides, so P2 is equals to P1 exponential minus G Z2 minus Z1 over RT naught. So this is an expression provides the desired relationship between the pressure elevation for isothermal layer, that how the pressure changes as the elevation increases in the case of gases. For a non-isothermal condition, a similar procedure can be followed if the temperature elevation relationship is known. The equation we derive in the previous slide, an important application of this equation relates to the variation in pressure in the Earth atmosphere. Ideally, the measurement of pressure versus altitude over the specific range for the specific condition. Based on the specific condition, a standard atmosphere has been determined that can be used in the design of aircraft, missiles, and spacecraft, and in comparing their performance under standard condition. Currently accepted standard atmosphere, so-called US standard atmosphere, which is an idealized representation of middle latitude year round. As is shown in the figure below, the temperature decreases with altitude in the region nearest the Earth's surface is called troposphere. As shown in the figure, the temperature decreases. Let's see the next slide. Here you can see the temperature decreases as the altitude is increasing. Okay, so from here to here where the temperature is decreasing with the altitude, such layer is called troposphere. So here, as shown in the figure, just we have noticed the temperature decreases with altitude in the region nearest the Earth's surface is called troposphere. Temperatures become essentially constant in the next layer is called stratosphere. So here is the next layer where the temperature is constant after that, and such layer is called stratosphere. And subsequently start to increase in the next layer, and further the temperature start increasing with the elevation. Typical event that occurs in the atmosphere are shown in the figure in the margin. Let's see. Here is the behavior of the air density. It is initially increasing at the elevation is increasing, okay, and then the temperature is constant. After the stratosphere it is increasing and then further increasing very sharply, and then again it is being constant. Based on such observation we can say that, so what is the standard atmosphere tells us? In the atmosphere, density and temperature varies continuously, okay. The change from day to day and place to place, definitely, because based on the place and every day it changes. Moisture also plays part in the variation of air density and temperature. However, the influence of moisture is small and generally neglected in practical calculations, okay. The changes due to the influence of moisture we do not consider in the practical calculations. So we normally consider the changes due to the pressure or the temperature, and for that we have derived the equation in the previous slide. In the field of aeronautical engineering, to avoid the difficulties arises due to density variation, an international standard atmosphere is selected, that is at sea level these are the values are considered, okay, varied up to altitude 11,000 meter. Above this altitude the temperature is assumed to be constant at A, and this value is valid from 1000 meter, okay, because the temperature increases with a gradient of 6.5 degree up to 1000 meter, and after the 1000 meter it become constant as shown here. This is the 11,000 meter. Up to here it is increasing with the gradient 6.5 degree per kilometer, and after that from 11,000 meter it become constant up to 20,000 meter. So here are the some standard value that has to be remembered, and now we are going to see the measurement of pressures. How do we measure the pressures and what are the pressures normally we measure? That also we have discussed in the previous slide. So let's see, numerous devices and techniques are used to measure the pressure, okay, and what are the type of pressure we measure? The pressure at a point within a fluid is designated as an absolute pressure or gauge pressure. So either we measure absolute pressure or gauge pressure. Gauge pressure may be negative pressure or positive pressure, or the negative pressure is also called the vacuum pressure. Absolute pressure is measured relative to the perfect vacuum, and the gauge pressure is measured relative to the local atmospheric pressure. Most pressure measuring devices, however, are calibrated to read zero in the atmosphere. Normally the gauges we see in our daily life, that is in the on the compressor, on the water meter, normally they show us the gauge pressure. Those are measured with the reference of atmospheric pressure, and so they indicate the difference between the absolute pressure and the local atmospheric pressure. Now the measurement of atmospheric pressure. How do we measure the atmospheric pressure? The barometer is the device used to measure the atmospheric pressure. The simplest form of a barometer consists of a glass tube, as it is shown here. This is the glass tube, closed at one end. It is closed from the top end. The tube is essentially filled with mercury. We filled with the mercury separately and then turned upside down in the container of mercury, and then we turn upside down in the mercury here. Now this is the container which is open to the atmosphere. The atmospheric pressures are acting on the surface of the mercury which is in the container. The mercury column will come to an equilibrium. So as we make it upside down, due to the pressure difference, it goes ups and down and finally comes to an equilibrium position where its weight balance the force due to the atmosphere. The weight of the mercury being balanced with the atmospheric pressure. Thus P atmosphere is equals to density of the mercury into height of the column. So if we multiply both of them, we can calculate the atmospheric pressure of the atmosphere. Here there is a question that is it possible to use water to measure the atmospheric pressure? Is it possible? Yes, is it possible, but the density of the fluid comparing to the density of the mercury is less. So in that case, the height of the column gonna be much more than that. So it is difficult to make such a long tube, but it is possible. Okay, but the height of the column will be 3 or 4 times greater than the height of the column of the mercury. So now we see the manometers. What are the manometers? The manometers are the pressure measuring devices based on the use of liquid columns in vertical or inclined tubes are called manometers. Mercury barometer is one of the type of manometers, and the other example of manometers are, in that piezometer is the most simplest one. Piezometer tube, U-tube and inclined tube manometers are the example of some other type of manometers. So now the piezometer tube. So what is the piezometer tube and how do we measure the pressure by using the piezometer? The piezometer tube is simply a vertical tube open at the top and attached directly to the container or a pipe in which the pressure is desired. So consider this is a container, okay, and we just directly connected with the pipe. As soon as we connected, the fluid comes out to the pipe, comes out to the tube, and the height of the column achieved. So let's move on, and it is open to the atmosphere. Okay, so this height of the column gives us the pressure available in the container A. So let's see how do we measure the pressure by using a piezometer. Consider a closed container. We make a hole here and we connected the U-tube manometer with the container. So now what we are going to do now, how do we measure? So this is open from the one end. The pressure, that means the pressure exerting at the top is the atmospheric pressure, because this is the free surface. At the free surface, the pressure which acts, that is the atmospheric pressure. So now what we do, we know that the pressure at A and pressure here is uniform, is the same pressure, okay, because the fluid is continuous. The fluid is continuous, and we can consider this is our reference point. Okay, since this is our reference point, so the moving from left to right, so we are moving from here to here. So we consider there is a pressure at point A that we want to measure. So pressure at A minus height of the, because we are going up, if we going up the pressure decreases. Okay, so minus gamma 1 H1, and this is the other side equals to P naught. So now PA minus P naught is equals to gamma 1 H1. So this will give you the gauge pressure. Okay, if you make the difference, because the what is the gauge pressure? Atmospheric pressure minus, absolute pressure minus gauge pressure, absolute pressure minus atmospheric pressure equal to gauge pressure. So this will give you the gauge pressure, and if you take this gamma 1 H1 other side, this will give you the absolute pressure. So that is going to be equal to gamma 1 H1. So then in terms of gauge pressure, the equation for a piezometer tube is equals to PA is equals to gamma 1 H1. So in case of the gauge pressure, the PA will be equal to gamma 1 H1. PA is equals to P1 because they are at the same level, because we are considering this is P1, or because the A and point 1 are at the same level, so we can say that PA is equals to P1. So here there are some disadvantage and advantage of this piezometer. So what are the disadvantages of the piezometer? It cannot measure the gas pressure. Definitely it is not, because if this container is filled with the gas and the piezometer is open from the one end, if the piezometer is open from the other end, what will happen? The gas will comes out and it will go to the atmosphere. We will not attain any height of the column. Okay, so the piezometer is not, so the piezometer do not measure the pressure of gases. It cannot measure high pressure so that the required height of the tube is reasonable. Okay, there is another disadvantage. It cannot measure the medium or high pressure, because if there is a high pressure, what will happen? The height of the column going to be very high. So if the height of the column is going to be very high, so it is very difficult to make such a long tube. Okay, so if it is 5 meter, 6 meter is the height of the column, and sometime we measure the pressure is 120 meter, 130 meter, so it is not possible to make a glass tube of 130 meter or 40 meter, even 10 meter or 20 meter. It is very delicate. So we do not use it for the high pressure measurement. Number 3, it cannot measure negative pressure. Otherwise air will be sucked inside. Also we cannot use piezometer to measure the negative pressure, because if the pressure here is less, so what will happen? All the air from the atmosphere will go inside and it will increase the pressure. So this piezometer is not eligible to measure the vacuum pressure. So how we can overcome these problems? To overcome such problems, we use another type of manometer that is called a U-tube manometer. So in case of U-tube manometer, what is the construction of U-tube manometer? U-tube manometer is a U-shaped tube, as we can see, that contains a fluid in it. Okay, so we use a fluid inside the manometer to avoid all those problems that we faced in the piezometer. Contains a fluid in it called gauge fluid. The gauge fluid must be immiscible with other fluid in contact with it. Two common gauge fluids are water and mercury. So this is the construction of the U-tube manometer, and this we use to measure the pressure, and it almost remove all the problems that we face in the piezometer. So let's move on to the other slide. Now let's see how do we measure the pressure by using the U-tube manometer? So this is the gauge fluid, or the blue one, and it is also called a manometric fluid, and there is a container in which there is a fluid that is maybe gas or maybe liquid, and it has some pressure PA. Okay, so now because of this pressure, initially the U-tube manometer, when if there is a tap or something, so initially the level of the U-tube manometer will be same, but due to the pressure in the container, it pushed the manometric fluid, and because of that the height of the column will achieve. So how do we measure the pressure by using the U-tube manometer? First of all, so there are two ways to measure the pressure by using a U-tube manometer. First of all, what we do, we take the lowest level of the gauge fluid or the manometric fluid. So this is the lowest level, so we consider it as a reference line. Okay, so now how do we measure the pressure? One way, we start from here and then continue up to other end. The other way, we measure the pressure of this side equal to the pressure of this side. So this is the reference point of this side, because the pressure here and pressure here is same. So there is no use to include the height of the column of this fluid from here to here, because this is a continuous fluid, the level is same, the height is same, so both of them will cancel to each other. So now we are going to do the first way. We start from here and then we continue and we go up to the top. So let's see, since one end is open, we can work entirely in gauge pressure. So you must keep in mind, during the measurement of gauge pressure, we do not consider the atmospheric pressure, because the atmospheric pressure is the reference pressure. If you are measuring the absolute pressure, so you have to consider the atmospheric pressure, you have to add up the atmospheric pressure. So now we are making an equation for the gauge pressure. For the gauge pressure, now we start from here, the pressure at point A, PA. So this PA, now there is a height of the fluid, okay, the pressure due to this height of the fluid. So the density of this fluid is gamma 1 plus H1. So we are going down. So down is positive. As you go down in the fluid, the pressure increases. As you go up in the fluid, the pressure decreases. That will consider negative. So you are going down, that means the pressure is increasing. So you are considering the positive, plus gamma 1 H1. Now you move to other side, because up to here the pressure is same. So now you are here. At this point you are going up. So since you are going up, so what will happen? The pressure will decrease. So minus gamma 2 H2. So this is minus gamma 2 H2 equal to 0. So since it is a gauge pressure, so we are considering 0. If it is if it is absolute pressure, so we consider P naught, or the absolute pressure PA. Then the equation become the following. So PA is equals to gamma 2 H2 minus gamma 1 H1. In the fluid in the container is a gas, then the fluid 1 term can be ignored. Okay, if the fluid in the container is gas, okay, so the height of the column, because the density of the gas is very low, so the component of gamma 1 and H1 can be neglected. This is the meaning here. So now notice, in the same fluid we can jump across from 2 to 3. They are the same level and thus must have the same pressure, as we have said that. Okay, the advantage of U-tube manometers are, it can be used to measure gas pressure, because the container is closed with the fluid. The gas cannot come out, gas cannot go out. Gas will push the fluid and it will give you a height of the column, and you can measure the pressure of the gas. So there is no way of the gas to go to the atmosphere. So by using a U-tube manometer, you can measure the gas pressure. If the pressure PA is large, then use of a heavy gauge fluid mercury can reduce the column height and vice versa. So U-tube manometer can be used to measure the high pressure also. Okay, if the pressure is very high, you can reduce the height of the column by using a very heavy fluid, which gives you a less height of the column. For example, the mercury. If the pressure PA is too small, then use a lighter gauge fluid. Water can provide easily readable column height. So almost all the problem, almost even now, U-tube manometer can be used to measure the negative pressure or vacuum pressure, because the U-tube manometer, the container is not open to the atmosphere. If there is a negative pressure inside the container, so height of the column will come this side. So it will, this column will come here and this column will come here, and it will give you a difference of height of the column at this side. So all the problems what we discussed in the using of piezometer is almost covered. So the U-tube manometer is most useful device to measure the pressure. So now the U-tube manometer is also used to measure the pressure difference between the two container or between the 2 points. So it doesn't only measure the pressure at a point, it also measure the pressure difference. For example, this is the 2 container, and if you want to know what is the pressure difference between the 2 container, or what is the pressure difference between the 2 points, normally it is very important application in the field that we do that. In the duct, in the air conditioning ducts, we measure the pressure difference across the valves, across the equipments. We want to measure the pressure difference, that how much pressure is being dropped by the equipment. So how do we measure the pressure difference? The procedure is same. So for the 2 container, let's see, for the flow between the 2 containers, the pressure equation will be, how do we measure the pressure equation? The simple procedure that we discussed before. Since this is container 1, this is container 2, and it is connected with a U-tube manometer, and this white one is the manometric fluid. Okay, the density of the manometric fluid is gamma 2, the density of the container 1 is gamma 1, and density of the container 2 is gamma 3. So the procedure is same. We take it, this is the lowest level of the manometric fluid, so this is our reference point. This is our reference point. So for that we start from here. So this is the pressure. This is the pressure at this point is A. So we are considering this is A, and the pressure due to height of the column gamma 1 H1, and then from here you move up. So this is manometric fluid, the height of the column. This is gamma 2 H2. So since we are going up, so it is minus gamma 2 H2. Again we are going up, so it is minus gamma 3 H3 is equals to pressure B. Or you can take minus PB is equals to 0. Or you can keep this is the container B, the pressure in the container B. So this way you can calculate the PA minus PB is equals to, take all the items to the other side, will give you the pressure difference between the 2 container. So in the same way you can calculate the pressure difference between these 2 points. So here also you will take the same procedure. This is the manometric fluid you can see here, and the fluid which is flowing with a particular pressure inside the pipe. So there is a pressure A and there is pressure B. So we want to know the pressure difference between these 2 points. Okay, because here you can see there is a orifice or there is a nozzle. Because of that there is a pressure difference, and this pressure change we want to measure between the across this nozzle. So the procedure is same. This is the lowest level that we are going to see. Okay, from here to here, from here to here the level is same. Okay, from here to here the level is same. So that means the pressure here, the pressure here, the pressure here is same. So let's see the pressure, initially the pressure PA, then we are moving up, the gamma 1 H1 negative because we are moving up, then the pressure at this point and pressure at this point is same. So we move to the point 3, the pressure here is also same. From here to here, this is the manometric fluid, this is minus, again we are going up. Okay, from this reference point again we are going up. So this is gamma 2 H2, and then we are coming down, we are coming down. Okay, so what is this height? This height is gamma 1, this is gamma 1 H1 plus H2. So from here to here the height is H1 and this H2 is equals to the pressure at point B. You can consider minus PB also, but you take as other side, so it is PB. So PA minus PB will be equal to H2 gamma 2 minus gamma 1. So because if you open up, they will cancel with each other, and then finally we end up with this equation. So now another type of manometer, that is called an inclined tube manometer. So what is the application of inclined tube manometer, and how do we measure the pressure by using the inclined tube manometer? The tube is inclined at an angle of theta, and the differential reading is measured along the inclined tube. So this inclined tube manometer is used to measure the pressure difference. Okay, the difference in pressure is measured as, so how do we measure the pressure? This is the manometric fluid, this is the manometric fluid. So here the same, we take the lowest level, we mark the lowest level, so this is the lowest level, and the pressure is the procedure is same. We start from here and whatever is the lowest level, and then we move up. So this is here, and after that this is the length L. So from here we start from here, this is pressure PA, and then gamma 1 H1 because it is positive, because we are going down. Then again from here we are moving up. So but we are not, we need a height of, vertical height of column. So vertical height of column, what would be the vertical height of column of this manometric fluid? So you take this as a hypotenuse, the angle theta is given, so this is the vertical height of the column. This is going to be sine theta, so it's going to be gamma 2 L2 sine theta. Then again you are moving up, so the height of the column is given from here to here, that is H3. So gamma 3 H3 is equals to PB, and then PA minus PB is the pressure difference between the two container. Note that the pressure difference between the point 1 and point 2 is due to the vertical distance. Okay, that we said this is the point 1 and point 2, we need a vertical distance. So this is the vertical distance, okay, we considered between the 2 points. Inclined tube manometers are usually used to measure small pressure difference in the gas pressure, where the contribution of gas column H1 and H3 can be neglected. It means this is used to measure the very minute pressure, very small pressure. If there is a small pressure, so you have a small deflection, but if you use a inclined manometer, so what will happen, you will get a more deflection. So this is used to measure the low pressure of the gas. So now we will see in our next lecture, we will solve some problems and we will see some application of the pressure gauges. Thank you very much. Assalamu alaikum.